So this function is not continuous at this point. Okay, yeah. Let's look at that. So here, y, I like to assume y1 greater than 0 for easy discussion. Yeah. If it is less than 0, yeah, we can also do another discussion. Yeah, but for simplicity, let's use the simpler case. All right. Then let's look at the check these three conditions. Yeah. For the first condition, limit x approaches 2 from the left-hand side, minus, okay, left limit. And what is the function y1 over x minus 2? What is this limit? Yeah. The numerator, because x smaller than 2, so x minus 2 is a negative number. But the x goes to 2, that means the denominator goes to 0. 0, but from the negative side goes to 0. The numerator is a positive number, we assume. Positive number over negative number is a negative number, right? But the whole fraction goes to infinity, right? So the limit is negative infinity. Okay, all right. Then the right limit, x goes to 2, but from the right-hand side, y1 over x minus 2. y1 positive, denominator also positive. Well, from right-hand side, so x greater than 2. X greater than 2. X minus 2 is a positive number, but this positive number goes to 0. Yeah, so denominator very small. Yeah. So y1 over a number that goes to 0, it's infinity, right? Infinity, but the sign is positive. Positive over positive. So the limit is positive infinity. Okay? Yeah? Then, negative infinity, do we treat this case negative infinity, do we treat the limit exists or not? No. Because when we say a limit exists, it must be a concrete number. It cannot be infinity. Infinity, we do not treat infinity as a valid number. Okay? So the first condition is violated. Okay? All right. Positive infinity, it's not a valid number. So we do not say the limit exists. Okay? So the second condition, oh, sorry. Yeah. Also, oh, what's wrong? Yeah. Something. Yeah, all right. Yeah. The second condition also violated. Right? Yeah. Then we don't need to check the third condition, right? One of the conditions violated, then the whole thing is gone. Yeah. No continuity. Yeah. Although the third condition, if you check, yeah, and another thing, yeah, if you really want to look at the third condition, the function is, so here, the third condition, the function must be defined at x0 point. Here the function is even not defined at a x equals 2 point. It's not defined. No function value there, right? So even the third condition, yeah, far away. Yeah. So here I just want to, review your calculus knowledge a little bit. Okay, yeah, small chance. Yeah. Review this knowledge. Yeah. All right, let's go to the next slide. Yeah. Yeah. But I will not, give you test, quiz, homework questions like this. Yeah, just for your understanding. Yeah. Otherwise, yeah, because I don't want to give you calculus questions. Okay? Yeah. Still, the material targeting our ODE, PDE, ODE content. Yeah. All right, B.3. Now, let's look at the uniqueness theorem. But let's look at the first order. Yeah, yeah. This linear may not be linear. Okay. Yeah. So this linear, yeah. I just, yeah. I should remove this now. Yeah, because it may not be, many times may not be a linear ODE. Yeah. All right. Now, initial value problem. Yeah. So here you can see. Yeah. The first two lines the same as the existence theorem, yeah, that of the existence theorem. Then, now, the properties, yeah. So we require, okay, a little more properties, yeah. The properties, different, yeah. First condition, yeah. So continuous, the same as that previous theorem, continuous, yeah. All points, yeah. Second condition, this time we need to use partial derivative. F sub y is continuous at all points. Yeah. So this extra condition for uniqueness. Yeah. Extra condition. Yeah. Yeah. All right. Then the third one, bounded. Yeah. F1 bounded. Yeah. So this part and this the same as in the previous theorem, but the extra conditions, second condition, and this part. Partial derivative, f sub y, also bounded in R. Yeah. All right. So, conclusion. Yeah. Yeah. Yes. Yeah. Conclusion. This initial value problem has at most one solution. Okay. The first part, at the most 1 or 0, yeah, because it may not have solution. Yeah. So at the most, one solution, less than or equal to one solution number, but you cannot have two solutions. Yeah. So here, this is the uniqueness part. Yeah. If you have solution, the solution must be unique. Yeah. But how do you eliminate the 0 case? Yeah, because less than 1 could be 1 or 0. Okay, in 0 case, yeah, because our previous theorem we already have the first condition. We also have the second condition. So we automatically have the existence part, right? Yeah, we have the existence part. Yeah, that's why. Furthermore, we use the existence theorem so we can improve this conclusion. Yeah, improve this in this way. It has exactly one solution. That means the 0 case is gone. We eliminate 0 solution case. Yeah, because we have the existence part. Yeah. Yeah. So this theorem tells us you need to check these 3 conditions. If all 3 conditions are satisfied, then you have both existence and uniqueness. So that means it has exactly one solution. Okay? Yeah. That's the first order ODE. Yeah. Then our second order ODE, yeah, we will have partially similar, yeah, but we need to change some other parts. Yeah. All right. Yeah. Example, existence and uniqueness. Yeah. Let's consider this initial value ODE. Yeah. Here you can see regarding the y part, it's not linear. Yeah. So that's why, yeah, not necessarily linear. Yeah. Okay. All right. Solve the equation. Yeah, because this is so simple, we can solve it. Separable. Yeah. Type. Yeah. So, and we can find the solution. This is the solution, right? Yeah. This is the solution. Okay. Yeah. All right. Yeah. So, and yeah, so the initial condition, y of 0 equals 0, tangent C equals 0. So what is that C? Yeah. 0, pi, 2 pi, right? Yeah. Integer multiple of pi. Yeah. C equals k pi. Okay? Yeah. So tangent of k pi, 0. Right? See? Yeah. Pi periodic. Yeah. So the solution is y equals tangent of x. Yeah. So you have the solution. Yeah. All right. So here, consider x in this interval. Yeah. All right. But the other side, we want to check the conditions in the previous theorem. Yeah. All right. So rectangle area R. All right. AB to be determined. Yeah. All right. Yeah. Yeah. So in a textbook, A and B, yeah, use these two simple numbers. Yeah. All right. Here, because we can do a little different, so I put a AB to be determined. Okay. So we can make some change when necessary. Yeah. First, f function. Yeah. So continuous, very easy. Yeah. Continuous. Then bounded. Yeah. So it's bounded. Okay. Yeah. So the constant b. So this is bounded. Yeah. Existence. Yeah. After these two conditions, continuous, bounded. So existence. Yeah. Because we need to, use this alpha number based on the existence theorem. Okay, all right. Yeah. Yeah. And yeah, so here I put we want this interval as large as possible. Yeah. Alpha as large as possible. Okay? Yeah. 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 All right. The larger the better, right? Yeah. All right. That means so let's look at this number. Yeah. All right, yeah. How to make this number as large as possible. Okay, yeah. So here, undetermined, yeah. So here we choose 3. Yeah. If we choose a number different from 3, can we make the value of this fraction larger? Yeah. Some small math practice. Yeah. All right. Here we write this version. 1 over b plus 1 over b. Okay? So the denominator is b plus 1 over b, the special structure at the denominator. Our goal, we want to make this whole fraction the largest. The larger the better. Yeah, the whole fraction. Yeah. The larger the whole fraction, the smaller the denominator, right? Yeah. 1 over some number. If you want to make this whole fraction the largest, you should make the denominator the smallest, right? So now the question, what is the smallest possible number for the denominator? Yeah. So that's an interesting question. When you choose b, for what b, you get the smallest possible denominator. That question. Yeah. Make as small as possible. Yeah. There is a famous inequality called the mean inequality. Yeah. Here. Mean inequality. Yeah. Mean. Yeah. The meaning of mean. Okay? Yeah. All right. Have you seen this inequality before? Yeah. This is the simplest version of mean inequality. The left-hand side we call arithmetic mean. It's a mean. What kind of mean? Arithmetic mean. Okay? Arithmetic mean. The right-hand side, another mean, different mean, geometric mean. Geometric mean. Okay? So this mean inequality tells us arithmetic mean is always greater or equal to the geometric mean. That's the well-known theorem. Okay? Mean inequality. Yeah. All right. So here we can apply the mean inequality. Okay? Yeah. 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 So AM greater or equal to GM. Yeah. Arithmetic mean greater or equal to geometric mean. Yeah. All right. Here you can see the product of these two is 1. Yeah. B, yeah, so here we can write B plus 1 over B over 2, arithmetic mean, right? Greater or equal to root of B times 1 over B. After cancellation, it is 1. Okay? Yeah. That means the B plus 1 over B is always greater or equal to 2. Okay? Yeah? That means the minimum is 2, right? Yeah, the minimum is 2. So when B equals 1, you get the minimum 2. Okay? You get a minimum 2. That is, so this interval, the largest possible number B over K is 1/2. Is 1/2. If you want to make the interval large, yeah, so the largest you can get 1/2. Yeah. So here just give you some interesting result. Yeah. So this inequality is very large. Okay. Yeah. Yeah. Some yeah. So I just use 2 or 3 more minutes to show you why this mean inequality is very useful in our everyday life. Yeah, very useful. All right. Let me give you a simple example in our real life. Yeah. Suppose you want to, make your fence around your yard. Okay. Yeah. Suppose your yard has a, rectangular shape. Okay. Yeah. X, Y. Yeah. The side, X and Y. All right. Under the assumption, because you need to buy the material, the fence material. Yeah. So how many yards, total yards to make your fence? Yeah. If it is known that X plus Y is a fixed number, okay? Yeah. The perimeter of your, fence, 4 sides, you add up 4 sides, is a fixed number, okay? Then, so when you make your fence, you want to make the area the largest. Yeah, the larger the area, you have, you can do more, okay? So your goal, you want to make your, the area inside the yard the largest possible you can cover. Okay? All right. So now the question, how do you choose X and Y? Yeah, because you can freedom to, choose X and Y, right? Yeah, freedom. So how do you choose X and Y to get the largest area? Largest area. That question. Okay? Yeah. You can use this theorem to get your answer. Okay? Yeah, because the total area is the area A equals A, the area, okay? B equals X times Y, right? Yeah, product, X and Y, okay? X and Y, do you have X plus X times Y less than or equal to X plus Y over 2 squared? Okay. Because here you take square both sides. You take square both sides, okay? So root and square gone. AB, you use XY. Okay? AB, you replace AB by X and Y, all right? Then A plus B over 2, by the assumption, that's a fixed number, right? X plus Y, A here, over 2 square, it's a fixed number. So the area can never be greater than this A over 2 square. The area is always bounded by this A over 2 square. And under what situation the area is largest? Yeah, because this inequality takes the equality case where A equals B. A equals B. The equality holds. So that's here. That when the equality holds, X equals Y. X equals Y. That means, yeah, so you make X equals Y. So it's a square shape. So when you make the square shape, then you get the largest possible area. So that's, this inequality tells you. Okay? Yeah. 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 So all right. Yeah. And here, yeah, because here, if you use given in the textbook, the largest alpha you can get, you plug in 3 because B equals 3. 3 over 1 plus 3, that's the 0.3. But we get a larger one, right? 1/2 is the 0.5. Okay? Yeah? So if we choose B equals 1, we can get a larger alpha. Okay? Yeah. So things like that. Okay? Yeah. All right. Yeah. 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 All right. Yeah. Yeah. But that's the existence part. Uniqueness part, yeah. Partial derivative, right? Yeah. So partial derivative, first continuous, second bounded. Yeah. So we can check those conditions easily. So we have both existence and uniqueness for this ODE. Yeah. Yeah, because here we get solution. Yeah. Unique solution. Yeah. All right. Yeah. Just some simple example to use to apply the theorem. Yeah. All right. Yeah. B.4. Yeah. This time we need to move to second order linear ODE. Yeah. Initial value problem, existence uniqueness problem. Yeah. All right. This time we may need that linear. Yeah. Yeah. The first order we do not need the linear. Yeah, because second we may need this condition. Yeah. All right. Homogeneous. Yeah. So this is linear, right? Yeah. So yeah, homogeneous linear. Yeah. Initial value problem. Yeah. If P function and Q function are continuous function on some open interval I, and x0 is in this interval, then the above initial value problem has unique solution on this I. Yeah, so simple, right? Here, it has unique solution that covers both existence and uniqueness, right? Yeah, see? Yeah, yeah. you can see the condition, P of x, Q of x, you only need a continuous condition. Then both existence and uniqueness. Yeah, so that, the theorem is so simple here. Okay, all right. Yeah, so if these two functions are continuous on open interval, yeah, has a general solution. Yes, yeah. So we try to put a little more. Yeah. Now we want to look at the general solution on this interval. And every solution, yeah. So here we try to do more. Okay, all right. Every solution, capital Y, yeah, on I is of the form linear combination. Yeah, we get to this. Linear combination, capital C1 times Y1 solution, and the capital C2 times Y2 solution, where Y1, Y2 is any basis of the solution. Yeah. Yeah. So for this part, we need linear. Yeah, because otherwise we cannot get this result. Yeah. Basis. Yeah. All right. Yeah. So here, yeah. So this part. Yeah. So because there is a concept called singular solution. Yeah. I will explain the concept sometime later. So here, there's another conclusion. Yeah. No singular solution. Yeah. But I will explain that concept later. First, I need to show you an example that has a singular solution. Okay? So then you will understand the meaning of the singular solution. Yeah. Singular solution, yeah, because when we talk about general solution, there is a formula, right? Yeah. Singular solution, that means that solution is not covered in that general, the form of that general solution. You cannot cover that. So singular, outside. But it's possible. Yeah. So you will see an example, singular solution example. Yeah, so here you can see solutions not obtainable from a general solution. Yeah. You need to use other different ways to get solution. But in other words, you can see the general solution may not be able to cover all the possible solutions. Sometimes, yeah, some singular solution cannot be covered. Yeah. All right. Yeah. Next, B.5. Now, yeah. So this one, Wronskian for linear independence. Wronskian, a special. Yeah, structure. Yeah, Wronskian. Yeah, we need to learn that. In last class, when we talk about how to check if two given functions, form a basis, yeah, sine, cosine, two functions form a basis. Yeah. I didn't give you the way to check how to check it. But I record so last night I record a video in the second further explanation for part A, 2A. 2A. Yeah. So in the second further explanation video, I explain why cosine x and the sine of x form a basis. Okay, 12-minute video. Yeah, I did a calculation. Yeah, all right. But here we do the general. Yeah, because that's a special function, right? Yeah, yeah, that's two special functions. But here, this topic B.5, we will discuss the general checking method. Yeah, yeah. All right. Yeah. So let me talk about that. Linear independence of solutions. All right. Homogeneous second order linear ODE. Yeah. We assume we have two special solutions, y1, y2. All right. Assume that y1 and y2 are two of the solutions of above ODE, but if they are linearly independent or not, we don't know. But we want to find it. Under what condition they are linearly independent? Under what condition they are linearly dependent? Yeah. Here we need to answer that question. All right. Yeah. So here we consider some open interval I. Yeah. We don't need to specify what open interval I. Yeah. It's not important. Yeah. Just certain interval I. Yeah. It's good enough. Yeah. All right. Interpretation. We need to compare it. Look at the linearly independent condition description here. Yeah. We call y1 and y2 linearly independent on I if the equation k1, yeah, so there exists constant k1, k2 such that the linear combination of these two solutions on I implies that k1 must be 0 and k2 must be 0. In other words, if one of the two numbers in k1, k2 is non-zero, then this expression cannot be 0. Yeah. If this expression equals 0, but it must be on this whole interval I, not just at one point. Now, here we understand this equality holds not just at one point, yeah, like x0 point, okay? Only one point. Then it's not strong enough to get a linearly independent property. So it must be on the whole I. What's the difference? One point and the whole interval. Whole interval, you know, all the point whole interval. 0. Or 1 point. Actually, you can find two functions linearly independent, but it can take 0 at just 1 point inside I. Yeah. You can find those examples easily. Yeah. So try to see the difference. All right. Here, okay, now we try to derive the critical condition here. Yeah. All right. This, now, we treat the left-hand side linear combination, we treat it as a function. How about that? Yeah, it's a function. It's a new function. Okay? All right. So this function equals 0 on the whole interval. Yeah. So this function, yeah, here, this is a function, right? Yeah. Some function. And this function equals 0 on the whole interval. Yeah. So if I draw the graph of this function, this is the graph. Okay. Suppose we have an interval I. This is the interval I. Okay. And this function, yeah, this function, could be, outside the interval could be anything, right? Outside the interval could be anything. But inside the interval, it must be 0. Okay. It must take this 0 inside this interval. So the function is like that. Okay? If the function is a constant 0 inside this interval, yeah, because the solution, so these two solutions must be differentiable, right? Y prime, y double prime. the solution must be twice differentiable, right? You can take double prime, twice differentiable. So the first derivative must exist. Yeah? All right. Now, let's take the first derivative of this function. What do you get? The first derivative of this function on I interval. What do you get? The first derivative of this function at on I interval. What do you get? 0, right? Derivative of the constant 0, also 0, right? Yeah. So let's take the first derivative of the left-hand side function on I interval. So we get a k1 y1 prime of x plus k2 y2 prime of x equals 0. So we have two equalities here. These two equalities. Yeah. Here you can see we start from one equality, but when we take a derivative, we get two equalities. We get another equality. That's interesting. That's useful, right? So the next question. Now, we need to use these two equalities together. Here, together. So we write a linear system. Is it a linear system? Okay? So we write this homogeneous linear system. Okay? Can you see homogeneous linear system? Because the right-hand side both 0, in linear system we also call it homogeneous. Okay? Yeah. Right-hand side 0. So we get a homogeneous linear system. Okay? Yeah? All right. Then, in this linear system, okay, what are unknowns? What are knowns? Yeah. What are unknowns? Because K1, K2 are unknown, right? Okay, well, two parameters to be determined. K1, K2. We do not know K1, K2. Okay? So K1, K2 are two unknowns. Y1 function, Y2 function are known functions, right? Sine, cosine, for example. Yeah. Two solutions are known functions, right? Yeah. We treat two solutions are known functions. So Y1, Y2 functions, they are known functions, but K1, K2 are unknown parameters. Here. So we need to solve this linear system for two unknown parameters, K1, K2. How to solve this linear system? Okay. Here we need to use linear algebra knowledge a little bit. Linear algebra knowledge a little bit. All right. So now apply the linear algebra knowledge. This linear system can be written in a matrix form. Okay? The coefficient part is a 2x2 matrix. Okay? Yeah. So y1 function, y2 function, the first row, the second row, y1 prime function, y2 prime function. Yeah. So we treat the coefficient matrix is known, yeah, because these functions are known. Okay? Sine, cosine, they are known. Okay? All right. But K1, K2, these two parameters are unknown. Yeah. So we want to solve this linear system, this homogeneous linear system for two unknown parameters, K1, K2. How to solve the question. Okay? Any interesting result we can use from linear algebra to give us some interesting observation here. Okay? Yeah. All right. Yeah. So let me give you critical property you need to apply here. All right. Determinant. So the vertical bar, around this matrix. Determinant. Okay? All right. Yeah. So here we need to use the determinant of the coefficient matrix. Because from the value of its determinant of the coefficient matrix, it can tell us on the worst situation, you can find the K1, K2, and on the worst situation, you cannot find K1, K2. That result is useful. Okay? That result is useful. All right. Now, let me tell you the final result. Yeah. First, I assume you know how to calculate the determinant, right? Yeah. So here I assume.
Yeah. Y1 times Y2 prime minus Y2 times Y1 prime.
That's the determinant formula. Okay? For 2 by 2
Yeah, let me write it right here.
Yeah, because it's very easy. So this determinant, the way to calculate. So Y1, the main diagonal numbers, Y1 times Y2 prime minus, that diagonal, yeah, So Y2, yeah, Y1 prime. Okay, so this is the determinant formula. Okay, this determinant formula is when the determinant is non-zero. What's the conclusion? The conclusion is this homogeneous linear system does have non-zero solution. Non-zero solution. Have zero solution. Y1 0, Y2 0, it's a solution, right? Y1 both 0 is a solution. If any of, K1, K2, K1, K2, okay, K1, K2. If any of the two K's is not 0, one of the two is non-zero, then the left-hand side can never be 0. No. That's the result from linear algebra.
Okay, all right. The conclusion is, if the determinant is non-zero, the only solution
is
0, 0.
That's the linear algebra result. Okay?
Yeah. All right.
So when we apply this linear algebra result here, you can see.
So we go back to this linearly independent. In order to tell if Y1 and Y2 are linearly independent,
you only need
to calculate this determinant.
You can write out the determinant.
Okay? Yeah. If the determinant is non-zero on the open interval I. Okay, that's here. Oh, on I.
Yeah. Non-zero. Yeah. On I. Yeah. Yeah.
All right.
Anywhere in I. Okay, non-zero. Only 1 point. It's enough. Okay. 1 point non-zero is enough.
Okay. Then you have the conclusion. It implies K1 and K2 must be both 0. Then you can say these two functions are linearly independent. Okay? So here you can see this determinant is
important, right? Yeah. So that's the name. Yeah. Wronskian. The name
is this determinant.
This determinant is called Wronskian. Yeah. Yeah. All right. Yeah. So you use the
Wronskian to check if
the two solutions are a basis or not. Okay? Yeah, linearly independent, the basis or not. But this is for order 2 case. Order 3, Y1, Y2, Y3, you have the similar result. Y1, Y2, Y3, you need to write a 3 by 3
matrix,
to determine Y1, Y2, Y3. Y1 prime, Y2 prime, Y3 prime. Y1 double prime, Y2 double prime, Y3 double prime. Then you calculate that 3 by 3 determinant. If it is non-zero, then the 3 solutions form a basis. They are linearly independent. Yeah. So the Wronskian. Yeah. Then n by n also true. Okay? N by n also true.
Yeah. So here you can see. Yeah. Yeah. You have that result. All right. Yeah. Yeah. And this people also call a trivial solution. Okay. So this homogeneous linear system can only have the trivial solution. If one of the two, K1, K2, is non-zero, that solution we call a non-trivial solution. Okay. So both zero we call a trivial solution. Yeah. All right. All right. Yeah. All right. Yeah. So let's next linear independence. Yeah. Depends independence of solutions. All right. So let's leave it next time.